During last week's meeting for the Designing Data Intensive Applications Study Group, I was not exactly prepared with what I wanted to say to accompany my slides, so I'm taking a different approach this time. This video serves as both a recap and a summarization of both of some of the points made in both of the chapter and our meeting last week. So this chapter was a bit more boring or dry, according to a few people that joined us last Wednesday, and I'm somewhat inclined to agree. But chapter 4, which dealt with encoding and evolution, is still a pretty important topic. And if you recall from chapter 1, Kleppmann talks about evolvability, a subpoint under the key concept of maintainability. Building systems that are easy to adapt and change over time is pretty necessary for any application. And in most cases, it's inevitable, right? Your data can change, schemas can change, which entails your application code also changing. And in the case of large server-side applications, you might perform the staged rollout and gradually update all your nodes. And if you have a client-side application, say a mobile app, your user might not upgrade immediately or even at all. The point is that both old and new code and data formats can coexist, and backward and forward compatibility becomes very necessary. One person had actually lamented in our meeting that the author should have explained in more detail how painful ensuring evolvability can be, because dealing with errors due to mismatched schemas and the code that handles it can be pretty frustrating. So usually your application will work with data in both in-memory data structures and sequences of bytes that could be written to a file or sent over a network. And encoding and decoding between these representations is what's discussed in the following sections. Those terms can also be referred to as serialization or deserialization, also marshalling or unmarshalling. But as was pointed out, in particular with serialization, there are other contexts where those terms are used, and thus a bit of a nomenclature clash that the author clarified on. There are various language-specific data formats like the pickle module, if you're familiar, in Python, that are often very easy to use. However, that comes with the trade-off of being stuck with one particular language for a while, and both backward and forward compatibility are thrown out the door. And if you have others wanting to integrate with your systems, that's going to be a problem if they use different programming languages. And there are formats that are pretty popular, such as JSON and XML, um, and they're popular due to their human readable format, although the latter has quite a different and more complex appearance if you look at the picture to the right. However, there can be some ambiguity, one example being JSON's representation of numbers. In addition, neither formats have support for binary strings, but nonetheless, they're still widely used, especially JSON. And lastly, in this section, Kleppmann talks about binary encodings such as Avro, Thrift, and Protobuf, which offer the benefits of compactness and data type guarantees. Typically, these formats require that a schema be created with an interface definition language and classes to use in your code that are made with a code generation tool. Only a few people in the study group actually use some of these formats, judging from our last meeting, but their schema evolution capabilities can provide some flexibility. One example of that being Avro, which works with the concept of reader and writer schemas. So the application encodes data and sends it over the network using the writer schema and receives and decodes incoming data, which has its own schema, the reader schema. And the flexibility part comes in that the writer and reader schemas don't necessarily have to be the same and only compatible. Since they don't have to be the same, only compatible, the Avro library can resolve the differences between the two. There are some questionable barriers to schema evolvability in protocol buffers, namely the required and optional markers for schema fields that Kleppmann discusses. And during our meeting, we were linked to a great post on Stack Overflow over here that elaborated on the issue. And outside of all that, the schema is also a great form of always updated documentation, which I found personally cool. So if you want to send some data to another process that you don't share memory with, you got to encode it before sending it, right? And the process on the other side needs to decode it. And in this section, Modes of Data Flow, Kleppmann talks about common ways data flows between processes. So he starts off with databases which can have multiple processes accessing it at the same time with various versions of code. Or a singular process could be both writing and reading to the database, in which you can consider it almost like writing a message to your future self. So both backward and forward compatibility still come into play here, but what struck me is how that both old data and new data can still live together in the database. A record that I could have inserted into a table moments ago, for example, could coexist with other records that I wrote a decade ago, right? Schemas can change, and most database tools have means of adapting to that. But the big idea is that data outlives code, or data lasts longer than code. Um, Luckily, schema evolution makes it appear as if the database was encoded with a single schema, despite older records from previous versions existing. Next, Kleppmann discusses data flow through services, starting off with the web services REST and SOAP. And by services, he means the exposed API that a server provides to a client in what is known as client-server architecture. And while it seems that the most popular way to design web services today is through REST, SOAP is still used mainly in enterprise, though those familiar with SOAP in our group did mention it is rather awkward and troublesome, as the book also states, further pushing along REST's popularity. SOAP also relies on code generation tools, whereas REST requires less tooling, though there are tools available such as Swagger to describe APIs and produce documentation, which the YouTube NLP team in SoS uses. RPCs, or remote procedure calls, are another way of making requests for services, though they are designed to look the same as a local function call, which carries a whole host of problems. As Kleppmann writes, there's an entire list on one page. But one example being the unpredictable nature of net requests and what they return. I actually had some trouble grasping the concept of RPCs, but these two articles over here were really useful to develop my understanding. There's usually a step involving the code generation of procedures for the client consuming the service, usually via some specification file. And lastly, Kleppmann discusses asynchronous message passing systems. So the idea is that if one process wants to send a message to another process, they pass it through an intermediary known as a message broker or message queue. And here's a diagram below. You can see the general process with a bit more jargon involved. Generally, the process sending the message is known as a publisher, who then sends their message to a queue, a singular queue or topic. The queue is then responsible for sending that message to each one of its subscriber processes, almost like how an email newsletter is distributed. And that's the end of my slides and video. If you have any input or other insights that you've gotten from reading this chapter, feel free to talk about it in the Data Intensive channel. And hopefully I'll see you in the next meeting.